Okay, so actually we have 2011 BC1 Form B. And in number one, they give us a cylindrical can. Has a radius of 10 millimeters. It's used to measure rainfall in Stormville. The can is initially empty. Rain enters the can during a 60-day period. The height of the water in the can can be modeled as a function S, where S is measured in millimeters and T is measured in days. And the time frame here is 0 to 60. And the rate at which the height of the water is rising in the can is given by S prime of T equals 2 sine 0.03 T plus 1.5. So that's our rate function for the can. And ultimately here in part A, according to the model, what is the height of the water in the can at the end of the 60-day period? So remember, keep in mind that this S of T function is a rate function. It's measured in millimeters per day. And ultimately, if we drew a picture of that function, millimeters per day versus days, okay, then we know that the area under that is going to be those two multiplied, so we get total millimeters. So it's an accumulator function because it's a rate function. So if we go from 0 to 60 of our S of T function, or S prime of T function, that is dt, okay, we would get the amount of water accumulated in the can. All right, and being that it's a calculator problem, we can go ahead and type it in. So we're going to go from 2 sine, 2 sine 0.03 T plus 1.5. 0 to 60, we get 171.813 millimeters. All right. Any questions on any part of that one? So ultimately, that part A here is worth 3 points. Okay. So the breakdown point-wise, where you had the correct limits. So if you had 0 to 60 on your integral, point. If you had the correct integrand, which is the rate function, another point. And if you had the answer, 171.813, got all 3 points. So I got 1 for the limits, 1 for the integrand, 1 for the final answer. So that one's 3 points altogether. Questions before we move on to part B? All right. Then in part B, it says, according to the model, what is the average rate of change in the height of the water in the can over that 60-day period? Show your computations that lead to your answer. Okay. So the average rate of change in the water, okay, is going to be, again, we have our change function, if you will, our S prime function that we used above here. Okay. If we want to find the average rate of change, then we need to ultimately figure out the amount at 60 and the amount at 0. And we're going to do 60 minus 0. Because remember, an average rate of change is just a slope. Okay. And remember, again, we're looking for the average rate of change in the height of the water. Okay. So if we knew the height at 60 and the height at 0, time at 60, time at 0, we can calculate our average rate of change. Now, what about this S of 60? So we know S of 0, I said the can didn't have any water in it at all at the start, right? So what about this S of 60 though? We don't have an S function, do we? No, isn't that the 171 that we just calculated? Remember, that is the height of the water at 60 days. So 171.813 minus 0, or 60 minus 0. And ultimately, keep that number in our calculator and just divide it by 60, we can get our average rate of change. So 2.864. And again, that would be millimeters per day. Now, just as an aside here, And just for the record, that's just worth 1 point on that one. So 3 for the first, 1 for the second part here. Think about how, just if you're not sure what you would do, you keep in mind that the average rate of change, any average rate of change is always going to be a slope, right? And if we have an average rate of change of our height, okay, then think about what the units are going to be. It needs to be some kind of rate. It needs to be millimeters per day. So how can we get millimeters per day? Okay, we do the 2 heights subtracted gives us millimeters. 2 times subtracted gives us days. So the division of those two, the slope between those two, would give us millimeters per day, which is, again, an average rate of change.
Can't you do one with the first one? You just put the 1 over 60 minus 0.
Yep.
In the first equation.
You bet. And the reason why is because, again, we have a rate of change function, right? Okay. So this is way number 1, if you will.
I'm saying part A at integral.
Right.
Isn't that basically just the same thing?
Well, if we do 1 over 60 times that same integral, is that what you mean? Yeah, that's what I'm saying, because that ultimately this is the rate of change function, if you will. And if we want the average of the rate of change function, we could just do we could treat it as an average value problem. And if we do that integral, we're ultimately going to get that 171, and what's it going to be? Divided by 60, we're going to get the same answer. So, like I said, which way is better? They're both reasonable. So if you thought of it as an average value problem, as long as you have that function that you find the average value of, then that's totally fine. Okay. And either way, you're going to get the same answer. So, all right. Questions so far? All right. Let's see about part C here. It says, assuming no evaporation occurs, at what rate is the volume of the water in the can changing at time 7? Indicate the units of measurement. So keep in mind that if we're gonna we know that we have a changing height here, and we know that we have, again, if there's water going into it, the volume is also changing of this water. So ultimately, that kind of makes it a related rates problem, then, doesn't it? So we know with the related rates problems, we need a function that relates our variables here. And in our case, the relationship here, since it's a cylindrical can, would be volume equals pi r squared h. True. And they also told us, though, that the radius of this can, which is not changing, no matter how high the water is, the radius is always 10, isn't it? So that makes it even a simpler formula. Just be 100 pi h then would be our relationship between the two variables. And then we know with the related rates problem, if we want to find out the rate of change of the volume here, we need dv dt. So that means we need to differentiate with respect to time. So our next step would be dv dt equals 100 pi dh dt. Okay. Now, again, we want to know dv dt when the h value is 7, I believe, right? No, when time is 7, sorry. Alright, so ultimately we need to know something about this. In order to figure out dv dt, we need to know dh dt. Okay. Well, isn't dh dt just s prime? Isn't s prime the rate of change of the height? Okay. So dh dt is s prime. So therefore, if we want s prime at 7, we can put it into that formula, which they gave us, 100 pi, and then what was it, 2 sine, 0.03 times 7, plus 1.5. And we get 602. Final answer here then would be 602, 218. Think about what would the units of measurement be here. What would volume be measured in? Be millimeters cubed per day. True? So ultimately, that part was worth 2 points. Okay, number 1, being able to come up with a relationship here between V and S, or V and H, if you will. We could have called it S from the get-go because they told us S was the height. I mean, as long as you can make sure you're clear that those two things are the same, that's fine. So if we establish a relationship here between V and H, or V and S, whatever you called it, it's worth a point. And then ultimately the answer was worth the other point. So 2 points total there. 6 so far. One might ask, how come when it specifically says to give the units of measure, how come we don't get a point for the units? Well, it turns out we do in a few minutes, because there's an answer point that if we got both units right in two of the different parts, we get an extra point for having the units right. So you may get points for that as long as you have it on the other part too, so we'll see that in a minute. All right, questions so far on the first three parts? All right, let's take a look at part D then. Part D, it says, during the same 60-day period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. This is the height of the water in the can on Monsoon Mountain is modeled by this function m. So this is our height function, 1/400, 3t cubed, 30t squared plus 330t. All right, and the height here is m is measured in millimeters, t is measured in days. And it tells us that that this d of t function is m prime of t minus s prime of t. Okay, so there's this new function d of t, that's the derivative of m minus the derivative of s. And ultimately, the work that we have to do here is to apply the intermediate value theorem to the function d on this interval 0 to 60 to justify that there exists some time between 0 and 60 at which the heights of the water in the two cans are changing at the same rate. Okay. All right, so ultimately here we need to take a look at what does this d function tell us. Well, again, this is the changing height for the Monsoon Mountain. This is the changing height for the Stormville can, right? Okay. All right, and so ultimately, if we were to figure out what would be d of 0, if you will. So the difference between the rates here at time 0. Well, if I put a 0 into the m function, I'm going to get what? I put a 0 into the m prime function, I should say. If we do our derivative, m prime of 0, s prime of 0, we make that calculation. So again, this is going to be the difference of the two rates at 0. So if I do my derivative command here, and so we get that figure. So 0.825, we'll say. I'll store that just so I have it. You know what? You're right. Sorry. So let's try that again. Minus. Turns out to be the same. So why not? All right. And then our s prime function, we already know that function itself. It's just 2 sine 0.03 times 0 plus 1.5, which we really don't need to calculate for that because sine of 0 is 0, so I'm just going to get 1.5. So if I do 0.825 minus 1.5, make it 0.675. Alright, so that's our d value at 0. Okay, and remember what we're trying to look at here is, let's go back and read the question again because I want to refresh what we're trying to find here. So we're trying to apply the intermediate value theorem to the function d on this interval to justify that there's a time between 0 and 60 at which the heights in the water are changing at the same rate. Now, just so we're clear on what we're trying to find here, in the procedure that we're, I guess, going to use here, if we're looking at the intermediate value theorem, remember the intermediate value theorem is generally used to determine that we have a 0 somewhere for our function. Okay? And so if the difference between the rates is negative at 0 and it's positive at 60, then what must have happened? Somewhere in between 0 and 60, the two rates the subtraction of the two rates had to equal 0, which means the two rates had to be the what? Wouldn't they have to be equal? The subtraction equals 0? And that's what we're after here. We're trying to show that these two rates at some point between 0 and 60 were the same. Fair enough? Okay. And we're doing it by, and they've asked us to do it with this d function, which is essentially the same thing, same question is answered by saying when the subtraction of the two is 0, that means that they have to be the same. Take something and subtract, we get 0, they have to be the same as one another. True? So ultimately, what are we hoping for here then when we do d of 60? We're hoping it's positive. True? So if we're hoping it's positive, let's see what happens. So if we do d of 60, that's m prime at 60 minus s prime at 60. So let's see what happens. Go back up and use my command I already had here and throw a 60 in there instead of a 0. And we get 72.825. And if we do the same thing with s, our s function, we got 2 sine of 0.03 times 60 plus 1.5. 3.447, and obviously that's going to be positive. We subtract, get our answer 69.377. Alright, so ultimately, again, by doing that, by showing that d of 0 is 60, okay, the difference between the two is negative, and d at 60, the difference between the two is positive. Okay, somewhere, since d is a continuous function, then it has to have crossed the x-axis, if you will, t-axis, I guess, in this case, which means that time would, at some point, the d value would equal 0, which guarantees that the m and the s functions, the rate functions, if you will, were equal, which is what we're after. Okay. All right, now, ultimately, there's two points to this. I'm going to tell you how what you needed to say to get the 2 points to make sure that we do it right. Ultimately, in the intermediate value theorem, again, recognizing that that theorem is generally used in really almost all of our contexts are to show that we have a 0, okay, between two x values, if you will. If we calculated these two values, the d of 0 and the d of 60, that was worth a point. Okay. So if we showed that it went from positive to negative or negative to positive, whatever the case may have been, okay, then we get a point for that. And then the justification, it's also worth a point. Now I guess there's a couple of key things in the justification here. When you write it, because ultimately, when you justify it, you need to write words for this. So you need to say something like this, since d is continuous, and this is an important point, because if you don't talk about the continuity of d, then the intermediate value theorem doesn't necessarily apply. So you need to say something like, since d is continuous, okay, and d of 0 is, I'll just put less than 0, and d at 60 is greater than 0, then the intermediate value theorem guarantees that some t between 0 and 60, d of t equals 0. And again, guaranteeing that d of t equals 0 is the same as guaranteeing that the two rates are the same, which is what we're after in the first place. Alright, so ultimately, another point for the explanation, if your explanation was correct. And again, keeping in mind, if you're going to use the intermediate value theorem, you need to make sure you know what that says and talk about the continuity, because it doesn't mean squat if there's not continuity. Okay. Alright, and so ultimately that's 8 points right there so far, and then the last point, like I said, was the units. So if you, in parts B and C, if you had the millimeters cubed per day, and the millimeters cubed per day in part B, remember earlier we put millimeters per day on part B, millimeters cubed per day on part C. If you had both of those units right, you got a point for that too. So like I said, total of 9. Alright, questions on that one?
Doesn't it ask what height on the last segment, and like which height is that first one?
Which one are we talking about?
The second one.
This part B?
Or is there a D?
we don't need to know the height. We don't need to find that value. Okay, we just need to show that there is a value that they're going to be equal, basically. Yeah, they don't ask us to find it. You know, if we had to find it, then we'd have to do a little bit more work. But all right, questions so far? All right, let's take a look at number 2 then. We got 2011 BC2 1B. Okay, this time we have a BC question. It's about polar curves. So we have a polar curve given, r of theta is 3 theta plus sine theta. So that'll be our polar curve. They also give us a stipulation here that theta here is between 0 and 2 pi, including both of those. Okay, so the first part here is just find the area in the second quadrant enclosed by the coordinate axes in the graph of R. So for part A, since we have calculator at our disposal, we put it in polar mode here, and we graph said function 3 theta plus sine theta. And in terms of our window here, the theta min, theta max should be on 0 to 2 pi like they told us. You can step it. You know, remember, it's just going to plot points every 0.1 if you have your step at 0.1, which probably is sufficient. Window-wise, I got to go from 0 to 5. I don't know what this thing looks like, so I'm going to change it -5 to -5, and then -5 to +5 in the y direction also. And we'll see what we see. And it looks like we need to move it a little bit higher to see what's going on up there in the second quadrant. And a little bit more to the left, of course. All right, so, and just so we can get a better idea of what the whole picture is going to look like. You can see that and one thing to consider here too is if this is the sign makes it periodic, but if we keep adding 3 theta to it, this is going to continue to grow, which is going to make it go away from the origin even more. This is actually going to create a spiral. Okay, so it's going to continue to go away from the origin with that 3 theta there. But we don't really care about that because all we're worried about here is the second quadrant stuff anyway. So remember that the general formula that we use here is we're going to go 1/2 r squared d theta on something to something here. All right. So the issue here is 2 things. Number one, we got to figure out what is our r. Our r, of course, is just the function itself. So we're going to have a half here. We're going to have 3 theta plus sine theta squared d theta. And then the other part here is we got to figure out what are our limits going to be here. In other words, if I start here at 0 for my theta value, 0 into my function is going to give me 0 plus sine of 0, so that's 0, 0. Started at the origin. We saw it travel here. Question is, where is it going to be back to that point, which appears to be pi over 2, and looks like 1, 2, 3, 4, 5, something. Actually should be, I don't know if my scale's on here, but let's do this too. We can look at our table. If we do table set here, and we do, I got it going by, starting at -pi over 2, we'll go by pi over 4s. We look at our table here, here's our 0, 0, and if we go our pi over 2 here, remember I told you it's by pi over 4 is the way I had it set up. Pi over 2 here gives us 5.7124, okay, which is ultimately that value that we saw right above. And remember, when we plot these polar points, we're plotting them in terms of a theta and a r. And if we put pi over 2 in here, that's going to give us 3 pi over 2 plus 1, sine of pi over 2. So 3 pi over 2 plus 1, you can verify yourself if you're not sure. Because again, it's a calculator problem. So if I do 3 pi over 2 plus 1, there's that 5.7 number. So that means that we do hit the second quadrant at pi over 2. That's where that curve starts to go into the second quadrant. And then the other point we'd want to look for is ultimately the pi point, because the pi point would be the angle that we're back and hitting third quadrant. And you can see that that's 9.42, blah, blah, blah. You could put that in there, put pi in here and pi in here, and we would get that exactly, which is 3 pi. So if we do that, that would give us our limits. Again, those are the angles where we begin to be in the second quadrant and where we end being in the second quadrant and go into the third. So with that, we calculate. Get 3 theta sine theta squared. And half of that, 47.513. And that should do it. Point breakdown should be 1 point if you have the integrand right. So even if you messed up the limits here, still if you got the integrand correct, get a point for that. Which hopefully shouldn't have been too tricky because we know the formula is 1/2 r squared. Right? So hopefully we got that point at least. Limits and constant, another point. So having the half and the pi over 2 and the pi over another point, and then final answer, get the third point. And that's that. Questions so far? All right. Okay, the next one then says for theta from pi over 2 to pi, which is that same region that we were just looking at, says there is 1 point P on the polar curve R with coordinates, with x coordinate -3, and it says find the angle that corresponds to the point P, and then find the y coordinate of the point P, and of course show your work that leads to the answer here. Okay. Alright, so keep in mind that when we have that curve that's defined in this polar manner, this r theta manner if you will, what we can do here is recognize that our x and our y, if we were to write them into our in the polar form if you will, our x and y coordinates anywhere on the plane, if we write this in parametric form, are going to be our cosine theta, our sine theta. Okay. Remember our relationship between x values and r values if you will. Okay. X's and y's, r's and thetas is going to be just that. Okay. And keep in mind that we know that this, we need to go down this path because ultimately we're looking for an x and a y value here, and all we have is an equation that has r and theta. True? So that doesn't really do us any good if we just have r and theta because we need some x and y. So we need some relationship between x and y and r and theta. Well, luckily we have such a relationship. We know that this is the case here. Now, we know then, and they told us that that somewhere between pi over 2 and pi, that the x coordinate is -3. So we know -3 equals, and if we put that equal to r cosine theta, and we try to solve for theta, because the question is ultimately what's the angle theta where this is true. Okay, our problem is we're going to have r and theta and then we're going to have two variables. True? So what about r though? What is r here in our problem? Isn't it this right here? So couldn't we write 3 theta plus sine theta times cosine theta? And then the only variable that we'd have would be what? Just be theta only, wouldn't it? Alright, so the question is, how do we solve this equation? Well, how much time should we spend on algebra solving this? None. Okay. It's a calculator problem, so don't solve an equation with algebra. It's not necessary. Okay. You can write the equation. Remember, one of the calculator things that you're allowed to use always is your solver, which is the 0 command, if you will, okay, or intersection command. So if we do that, and we graph these two, I would suggest putting it back into function mode. negative 3, and then 3x, parentheses, 3x sine x cosine x. And our window here, we went pi over 2 to pi, right? So see our solution there. Use our intersection command. Theta equals 2.017. Now keep in mind that we're gonna use this value to find another value in a minute, so I'd probably write down all of the decimals that I'm given there. Final answer wise though, I can just use the 2.017. Alright, and then now finally the next part here says find the y coordinate of P. So to find the y coordinate of the same point, we would use this. True? Well, we still don't know what r is in terms of a number, but we do know that r is 3 theta, well, sine theta, times sine theta. And so if we do our number that we have here, that 2.01692, etc., I don't know. I don't think that would work. I think I'd try it. Alright, so let's do 3 times 2.0169234 plus sine of 2.0169234. An answer for that. We'll multiply that by sine of 2.069169234. 6.272 is the final answer. So that would be the y coordinate of that point. Alright. And ultimately this part is worth 3 points also. Equation wise, you were able to write the relationship between x and r theta and be able to solve that equation. For writing the equation, you got 1 point. So 1 for that. 1 for actually finding theta, and then 1 for finding the y coordinate using the other equation. If you go back to just do a check in here, and if you go back to your polar mode and look at the graph of that, change my window. Sorry. So remember, we were looking at we were looking for a point that had an x coordinate of 3. So remember, even though this is graphed in a polar plane and the points are based on r and theta here, ultimately, if we found that point negative 3 right there, okay, you know, and look at our y coordinate that we found, does it seem reasonable at least? Negative 3 and 6, something. If we did a trace on this, keep in mind when you trace on this curve, if you trace it, it gives you values of theta and also x and y's, which is kind of convenient. And if we look at the closest we can get with that with the point ones that we have it on is negative 0.28, 6.28. So ultimately, you know, knowing that, being able to do that with our calculator, how does that, you know, help us with our analysis? You know, it gives a pretty good indication that we're right here, huh? It gives us a theta value of 2. Our theta value is actually 2.017. So just with that trace command, we could check that fairly nicely. Alright, anything else on part 2? So a total of 3 points, part B I should say. Alright, let's see if we can figure out part C then. So this time we have a particle that's traveling along a polar curve so that its position is x of t, y of t. such that d theta dt is equal to 2, and we want to find dy dt at the instant when theta is 2 pi over 3 and interpret the meaning of your answer in the context of this problem. So ultimately, again, we have our two equations that ultimately are going to come down here and be part of this part C also, because again, our coordinates are going to be found at any time given by, or any theta I should say, given by our cosine theta and our sine theta. Okay. All right, and so what we want to do is find dy dt. So keeping in mind though, if we know that if our y is equal to 3 theta plus sine theta times sine theta, okay. So that's our y in terms of theta. True. And if we want to know something about dy dt, it means we're going to differentiate with respect to time. So that means that our dy dt is going to be the derivative of this times d theta dt. So the derivative of this, we need to use the product rule here. So we did 3 plus cosine theta. Keep in mind that's going to be the, if I call that my first and that my second, to do the product rule. I'm going to do the derivative of the first. So keep in mind it would be that d theta dt times the second, sine theta, plus the second's derivative, which would be cosine theta, times the first, so 3 theta plus sine theta, and d theta dt. Again, we could just do the d theta dt all at the end too. Ultimately, we could just factor that back out and have the whole thing times d theta dt. Oops, there. Thank you. So again, ultimately, I did the first derivative times the second's derivative times the first, both times d theta dt. And ultimately here we want the answer when the 2 pi over 3 is our value. Of theta. Told us that 2 pi over 3, that's times 2 also. So if we go through and figure this all out, we got 3, and we can do this with a calculator at this point too, because it's a calculator problem, but ultimately 2 pi over 3 cosine is going to be small, so we negative 1/2 times 2 times radical 3 over 2, and over here cosine of 2 pi over 3 negative 1/2 again. 2 pi in here plus radical 3. And all said and done, that should work out to be negative 2.819. Right. So again, bottom line is really, it's ultimately kind of like a related rates problem. If we have a relationship between y and theta, which we certainly do, and we want dy dt, and we know d theta dt, we can just differentiate with respect to time. We'll introduce both of those quantities. And if we do that, then it's just a matter of plugging in the numbers. We know d theta dt is 2. We know theta is 2 pi over 3, that is. And if we punch out all those numbers, like I said, it's a calculator problem, so you can just do that all with the calculator, get negative 2.819. 3 points for this. I'll tell you, we didn't do the last point quite yet, but so far, just using the chain rule. In other words, recognizing that we have to differentiate with respect to time. Point for that. 1 point for getting the answer. So plugging the numbers in correctly and getting the answer after you do your derivative, hopefully correctly. And then the last part said, and interpret the meaning of your answer in terms of the context of this problem. Okay. So keep in mind this dy dt is negative 2.819 at this point. And ultimately, what does that mean? Dy dt is the change in y with respect to time, isn't it? So what's going on with our y values? Our y values would be decreasing at that point at a rate of negative 0.28, or at a rate of 2.819. And once again, going back to the graph, just for checking's sake, if we go theta is 2 pi over 3, which 2 pi over 3 is about 2 something, right? So here we are, let's say at 2 pi over 3 here, what's happening with our y values at this point? They're going up. They're going down, aren't they? Just for argument's sake, what if they had asked us about x? Should we have gotten a negative or positive with x? The state is getting bigger. What's going on with x right now? At that same point, x is getting more negative too, isn't it? Okay, any questions on that one? Alright, so ultimately again 3 points. One for the fact that you used the chain rule here by introducing the d theta dt and the dy dt. One for the answer. And then also one for the explanation that dy dt is negative. So the y coordinate. Decreasing.